seminar. So today we're very happy to have Marco Sangiovanni from the university to talk about generalization of Ohta's theorem.
Thank you so much, Lurie, for the introduction. And let me say that it's a real pleasure to be back in Princeton. And so as Lurie said, today I will be talking about generalizations of Ohta's theorem. And the plan for today's lecture, I will talk about first why. So mainly motivation for Ohta's theorem and some background. And then I will talk about what, meaning what is the main theorem that I will present today. And then in the third part of today's talk, I will talk about, how, meaning what are the tools that are involved in the proof of the what or with theorem. Okay, so let me start with one and giving some background about Ohta's theorem. So Ohta's theorem is about modular curves. So let me introduce the relevant notation. So we'll denote x1 and p to the r over q, maybe the compact modular curve of the level structure number 1 and p to the r. These are the matrices A, B, C, D in SL2Z that reduce to something such that, say, D is 1 mod n p to the r, and then C is 0 mod n p to the r. As usual, so just so that we're on the same page, the complex points are given by gamma 1 n p to the r modulo the upper half plane. And since I'm compact, we divide, I'm getting the costs. Okay, so then I will actually abbreviate XR as X1 and to the R. And then we're interested in somehow the tower of XR above XR minus 1 up until X1. So given this tower, we can consider the etale cohomology groups. So we have H1 of XR, QR with coefficients in ZP1. And now, well, you have the natural pullback maps, but actually the point of view of Ohta is basically reasoning with homology. And so you also have trace map from H1 down to XR minus 1, Q bar, ZP1 coefficients. And so now you have this projective system, and you have this sort of tower, which I will denote by of x infinity. This is the inverse limit under these maps. These are the transition map of H1 etale x to the r, still geometric etale cohomology with CP1 coefficients. Okay. So this is some sort of dual to completed cohomology, but only when you're looking at unipotent levels, so this type of level structure. So I just say what I mean by completed cohomology. H1 tilde etale of x infinity would be, first I take direct limit, then inverse limit of these guys. Okay, so then this, I guess in the literature, is sometimes denoted by the Borel-Moore homology of this tower. Okay, so this is almost the basic object of study. It's just that this object is still too large. And so we're gonna cut it down because here we have an action of certain operators. So on this space, we have on H1 tilde etale x infinity, we have an action of the operator UP, which is just the direct limit of the UP operator that you all know. And on this sort of object, the Borel homology, well, you have the adjoint, which is by UP prime, which is the adjoint of UP, and you can also describe it as some kind of Atkin-Lehner conjugate of UP. And then you have some additional structure, which are called the diamond operators. So basically at each level, gamma 1 and p to the r, you can look at the action of an element 1 epsilon for epsilon in z mod p to the r z cross. And the action of epsilon commutes with this trace map just by explicit description of what these trace maps are. And so here, this is also lambda modular, where lambda is ZP of ZP star. Okay. So this is the basic structure that we have. And so how we cut down this space is by taking an ordinary projector. So if you prime, you have E prime, which is just the limit of U prime and factorial over N. And so this I will define H1 Ohta, this is I will call the cohomology of, which is just U to this ordinary projector applied to this H1. Okay. So then I can state the theorem of Ohta.
Can I ask you a
Sure.
question? So you're saying that this cohomology group H1 et al. Under tilde is too large. Do you know anything about it as a module over, say, the Vassava algebra associated to this tower?
Okay, very good question. So you can I can describe it in terms of, say, let's reason with this one, and then this yeah. So basically, if you take limits over full level structure, then when you reduce modular identity here, then this is basically the invariance under the unipotent algebra. So then your question is very much related to what is the structure of the GL2QP representation after you take that n invariance. And I'm not sure what the answer is out of the top of my head, but I'm sure Lurie maybe can tell you. Yeah, maybe after this. So basically, there should be an answer, but I don't know it off the top. But so from the point of view, or just p-adic modular form, so this guy or this guy will see any finite slope form. Obviously, we would like to get something, let's say, finite over lambda. So we take the ordinary projector. Okay, so now let me state what Ohta proved. So H1 Ohta of x infinity is 3 over lambda. So sorry, here P is greater than 5. So let's assume this, you can reduce it to 3 with a little bit more work. Actually, our arguments later will give P greater or equal to 3. But so H1 Ohta is 3 over lambda, and it has a two-step filtration. That is GQP equivariant, which I will denote H1 Ohta x infinity plus. So this is inside, it's H1 Ohta of x infinity. And this has a quotient x infinity minus. So, and how do we describe these pieces, well, I have to tell you what the lambda structure is and what the Galois action is. So H1 Ohta x infinity plus as a lambda module is Hida ordinary Hecke algebra. And the GQP action is by the character epsilon sic, so the cyclotomic character. And then here, you remember I was talking about the action of lambda. And if I denote a diamond operator, so an element 1 epsilon, it's by the diamond operator associated to the epsilon sic. So it's this action here, and then the H1 Ohta x infinity minus is unramified. So wait, as a lambda module, it is isomorphic to the space of cost forms, ordinary cost forms, but p-adic, and GQP factored through the action of GQP factored through is unramified and acts by sending Frobenius to U prime.
Your action on the plus part, that's just the action of inertia, right?
Yes. Sorry, yes. So here it would be, yeah, thank you. And so here you have to take UP prime minus 1 if you want the full action. Thank you, Chris. Sorry. Okay, so so this is the basic comparison theorem. And actually here I should add the name of Fukaya-Kato. Because actually this isomorphism here, actually what Ohta basically shows is that this is isomorphic to as a lambda module to as that this tensor with ZP breve, and if I take GQP invariance, this is naturally the cost form. But then Fukaya and Kato construct the unramified period for this isomorphism. So this lambda module is isomorphic to whatever this is. Okay. This is Ohta. This is Fukaya. Okay.
What is phi goes to UP prime?
So the action is unramified and sends Frobenius to UP prime. So acts unramified. Okay, so now let me comment on this. Why do we care about such results? So, as Christian questions alluded to, well, so this sort of ordinary part of H1 tilde etale is a simple piece that you can cut out of completed cohomology. And so if you want to have a hope of understanding completed cohomology or homology, well, you might as well understand this ordinary piece, which is maybe easier to understand. And of course, completed homology and cohomology has many applications to the Galois theory, the theory of classicality of p-adic modular forms and representations, etc. So this is intrinsically interesting. And let me just mention that from this point of view, this module also has an action, of course, of the full Galois group, not just the local one. And so you can relate the Galois representations, at least if you localize at the maximal, suitable maximal ideal to the universal Galois representation. The universal ordinary deformation of a given residual Galois representation. So these are modules that really realize in some deep sense certain deformation properties of Galois representations. And then B, from the point of view of order systems, these type of results allow you to do two things. One is the freedom in varying the weight or your Galois representation that you're considering. So because if you can construct classes, Galois cohomology classes, not just, let's say, in H1 etale of XR Q bar with ZP1 coefficients, maybe you can show that these classes that you can construct are trace compatible. And so if you do this, now all of a sudden you have some sort of universal order system. So get some sort of and the description of, at least locally, of this as a Galois module should help you prove some explicit reciprocity laws. And so this is the point of view, for example, that is taken in King's Lesser-Zerbus in the case of their order system for a Rankin-Selberg convolution of two modular forms. But recently, this is also a two-way street, in the sense that here inertia acts trivially here by this non-trivial character. So most of the time, this will tell you that at least if you're away from Neben typus -1, then this extension will split. So this gives you a way in which to actually construct classes.
It was split in the category of GQP modules.
Excuse me?
As GQP modules were split.
Yes, because the inertia will split. So to I, it is two-way street. Meaning you can use this construct interesting etale homology classes, or rather families thereof. Homology classes in families. For example, let's say if you're familiar with what Cato's order system is, well, it uses some certain motivic elements, some modular curves or a product of them, which are called modular units. But for more general Shimura varieties, these modular units are not available. But the relevant etale classes are just GL2 Eisenstein series. So here, actually, I've given the theorem just in the case of the compact modular curve, but there's an analogous theorem for the open one, and there is an analogous result. And you can use this theorem really to give you canonical etale classes that are attached to this Eisenstein series. Okay, and these are integral. All right, so I hope that this is motivation enough. So,
Sorry, Marco, can you say a little more about how having this filtration lets you construct cohomology classes?
Yes. So let's say, okay. So here, let's say you have a theta series, okay, and P splits in the quadratic imaginary field that's attached to that theta series. So now you have a Hida family of the theta series. So it gives you an element in this S ord. But because of this isomorphism, you get a class in this quotient. Right? But then let's say if your Hecke character does not correspond to the Neben typus -1, then this this extension will split there. And so then this will give you a class here. Actually, a family of classes, one for each XR. Okay. So like this, you have constructed classes that are attached to a holomorphic theta series over GK. Meaning, well, if your product imaginary field is K. And obviously you can do this with isosine series if you're willing to. I haven't stated it, but if you're willing to accept that there is an analogous theorem with the open group. Okay, so want to generalize this picture for other Shimura varieties. Like you want to basically go beyond GL2. But so if you want to do this, well, then let's first analyze the key ingredients in Ohta's proof. And so we see why is it difficult to generalize. So, and actually we will see it in the very first step. And the very first step that Ohta does is interpret everything in terms of Jacobians. Of modular curves. Now you consider the connected etale for, well, the ordinary projection E prime of GR, where GR is the Jacobian of XR. So yeah.
So what's the inertia action on the middle term? So
Well, it's gonna extend this too.
I think then it induces some map from the quotient to the kernel.
Sorry, what is your question?
Because the inertia acts trivially on the quotient.
Yeah.
Right. So if I look at the action of the inertia subgroup, then it induces an action from the co-kernel. So this H1 minus to H1 plus.
Yeah.
And do you know what this map is?
So let's say you project to some weight. Well, if you get it's the, let's say your weight 2. Well,
No, weight 2 I can imagine is
Yeah.
split, but it's not split.
yeah, it's not split. It's not split in general. Yeah.
Yeah, yes. Okay. But I was just wondering, in terms of this description, what is this map?
Which one?
Map between what you were just released.
So I will say, so if you interpret this in terms of towers of Jacobian, this you map GR to its etale piece, the Jacobian to its etale piece, then the date module of that etale piece is naturally identified with the cotangent space of the Jacobian, and this is this map.
We can
Yeah. But so here, just trace, but the extension. So the extension comes out of exactly the disconnected etale sequence for this group scheme, and then you analyze each piece individually. So the conclusion is that Ohta's proof is very one-dimensional. meaning it's really for curves because that's how you understand the H1, it's through the Jacobian. Okay, so the general idea of this talk will be to replace the connected etale sequence on the Jacobian with something that always exists with, say, the Hodge-Tate decomposition. But of course, the Hodge-Tate decomposition is something really that's, I mean, until recently, really something that you have to invert P for. And so we want to use integral version of the Hodge-Tate decomposition of the etale cohomology, the middle degree etale cohomology of some Shimura variety. Okay. So I will write F2. So what? So maybe the most natural generalization of Ohta's theorem would be for something like Siegel modular varieties or Hilbert modular varieties. These are naturally the two type of extensions you maybe want to ask for. And actually we obtain the strongest results in the case of Hilbert modular varieties. So in this talk, I will focus on that case. So let me introduce F over Q to the real field. And let's say F over Q has degree D. Then I have, as before, Y1 and e to the R as the Hilbert modular variety. With level structure gamma 1 and p to the R, where n is instead the ring of integers of F is some ideal. And this level structure is the obvious generalization of the one for the GL2 over Q case. So Y1 and p to the R is the complex points are H and sigma F. I will say in a moment what sigma F is over n to the R, where sigma F is the set of embeddings of F into Q bar. Okay. Then as before, you have a tower. So maybe let me denote this by YR. So we have again our tower YR, YR minus 1, etc. And we can consider before the H. Now this time D, this is the middle degree of Ohta of Y infinity. This is the inverse limit under trace map. With ZPD coefficients. And actually, I will use this decoration here to denote interior cohomology, just because now if you want to compactify this, then the liberal compactification is not smooth anymore. So we will use this type of gadget here. This is just the image of compactly supported cohomology. And now, and so here I forget to ordinarily project. So here again, there is a UP operator that you can define. It's under that I did before. So now let me state the theorem. And this is always joined with Chris Skinner. Everything that I say today is joined with Chris Skinner. I forgot to mention at the beginning, but yes. So, and the theorem states the following. So if you look at HD Ohta y infinity and you take the inertial covariance and you tensor with ZP brev, take GQP invariance, then this receives a map from ordinary cross forms of dim level n. And this is, so it's an injection and Hecke equivariant and is an isomorphism after localizing at a good maximal ideal. Of Hida ordinary algebra. So good means the sort of so good means as in Karajanni Tamiozzo is a condition on the sort of residual Gallo representations that you allow yourself. Okay, so some comments. So after this afternoon, I think we can improve to split extension, splitting exclusion. And this is based on work of Zavialo. So this would be a direct summand of this. And so what is hard about this is what is hard to show that, say, it's an isomorphism, like in the Ohta case, is controlling H I Ohta of y infinity. So this is still here. So H I Ohta infinity when I is larger than D. So because this, the off middle degree, you will control basically, so will be a model over lambda, and when you quotient, say, by the augmentation ideal, who is to say that you get back the cohomology of the bottom piece of the tower. And so it's all about that, because we proved that at the semi-stable level, so if here you take just cos form of level gamma naught of p, then you can identify the two pieces. So it's really about controlling these sort of modules. But in the case of Hilbert surfaces, this is possible because the H1 is easily understandable. So theorem prime, so we get that S or NP to the infinity in trivial Nebentypus. So this means trivial Nebentypus. So the action mod P of the diamond operators is trivial. This is isomorphic to the trivial Nebentypus part. Inertial covariance. So when over Q is
I'm sorry, ZP2, what tilde means?
oh it's ZP breve, so this is just the bit vectors of F bar. So the valuation ring of maximum variation. Yeah, thank you for the question. And
So just to clarify something, you expect this isomorphism to hold true in general, but you can only prove it after localizing.
yes, so basically, yeah, localizing gets rid of all these guys.
I understand.
Yeah.
I understand, but you expect it to be an isomorphism.
I'm
I'm asking.
not sure.
Yeah.
I don't think anybody, has studied what kind of endoscopic families exist here.
You guys have no, so this is a split inclusion
Yes.
according to what you just proved today, right?
Yeah, and I mean,
You have no idea about the complement of this module S inside.
yeah, we can show that it has a trivial specialization so if you quotient by the augmentation ideal of lambda, that's 0. But yeah. But it really depends, and there is a spectral sequence relating the Tor I, the Tor J's of these guys to the reduction modulo something of this guy. And in the literature, nobody studies this thing at not a good maximal ideal. So this is why it's hard. Yeah.
You mentioned endoscopy, where does that come in?
It's just because, so here you expect, let's say you're on UN1, you expect the forms contributing to
Hilbert modular.
exactly. So there are none in that case, and Lurie has theorem showing that basically the complete cohomology away from middle is basically 0, but still there is no. It's very hard to say that there is nothing. For example, if you take U to 1, then we're working with Chris in the H1. There are some very interesting things here. Yeah, and so, but in general, yeah, how can you exclude the existence of these things? Because you cannot use automorphic tools because this is all integral and it's all about whether torsion accumulates or not. Yeah, yeah, no.
If you're on prime, you have H1, so.
Oops. HD.
Oh, okay.
I apologize. Is this HD? Yeah. Thank you, Naomi. Yeah, H2. All right. Any questions about this?
I'm still confused about what happens in the parallel weight 1.
Yeah.
Parallel weight 1.
Yes. So then by Q expansion, this space of modular form is one-dimensional. And what line do you get in this etale cohomology?
So do you get control theorem here? That is a degenerate weight, right? So it's a quotient. It's not inside.
I see.
Okay. Yeah. So otherwise, you don't get exactly an integral map.
Parallel weight, how does it come in? Yeah.
Parallel weight? No, it
If
doesn't.
you don't, you get more
If
general.
you're not, no, you cannot deform in non-parallel weight.
Oh.
This is the ordinary condition. Otherwise, you need nearly ordinary, and then, yeah, you need to be parallel weight. Yeah, very good question. Okay, so I guess this is an arithmetic geometry seminar. Right now, it's more like a number theory seminar. But so,
Okay, I'll leave now.
So this is based on an idea of Faltings that was greatly clarified by Bhatt. And let me take chance to thank him in person again for explaining this to us. So it's so then this is based on the prismatic cohomology as developed by so BMS, Bhatt Morrow Scholze, Bhatt Scholze, and Bhatt Lurie. So Bhatt. All right, so because BMS paper title is exactly integral p-adic Hodge theory, and as I said when I was talking about this is exactly the idea. Just replacing the connected etale sequence with the integral Hodge state decomposition. is about A, the Hodge state complex. So everything I will say here is in BMS. So let's say X is a formal scheme over O is OCP, and so I will denote X is the p-adic generic fiber. And so I also assume that this is smooth. And now this X has a pro-etale site. And there are certain important sheaves that so you have sheaves on X pro-etale that we'll use are going to be OX hat plus and A of X. So if so basis of the pro-etale topology are, let's say, affinode perfectoid, so spy of Ri plus, then the value of OX hat plus on U is just the completion of the Ri plus, and then Av of X at U is the bit vectors of the tilt. This, and so let's say X is puff O. So then you get A of X is essentially the A inf. This is Fontaine's ring. And is so it's the bit vectors of the tilt of OCP. So okay, and so but you can also describe this as the lim under X goes to X to the B of OCP, and so you have a map that is usually denoted theta from A inf to O, and the kernel of this map is principal generated by psi, which is usually denoted by psi. So now the main work of I guess BMS is focused on the following complex. So they define A omega X over O is going to be but I haven't defined U. Okay, so choice of primitive roots of unity, p to the r roots of unity will give you an element epsilon to the p to the r and in OCP flat. And now I'm taking a Teichmüller lift in A inf. And now I'm taking mu is this Teichmüller lift minus 1, and then psi, you can choose it to be mu over phi minus 1 mu. So who is A omega X? It's going to be this is called the décalage operator by mu attached to R nu star of A inf X. And who is nu? It's the projection of sites from the pro-etale site to the, say, the Tarski site of the scheme. Okay, so now I just have to tell you who is the décollage. Well, if I have a complex, let's say D of A-inf modules, then this is, and I say D is, little d is the differential, then these are the x's in mu dot of D dot, such that the differential, well, belongs to +1 of D dot. +1. Okay. Right? So, and then A in cohomology is going to be the define A in cohomology of X as the derived global sections of this A omega X. Now X of A omega X. And this is his cohomology theory. Is actually a special theory, cohomology theorem over O is the case of relative prismatic cohomology. As developed by Bhatt Scholze and Bhatt Lurie. So it will be for the prism A-inf, and then I have to specify a Cortini divisor here, which is the kernel of theta. Okay. So you have for each prism, okay. So, okay. So now what we'll be interested in is the Hodge tape complex, which is just going to be is just when you reduce modulo psi. I guess, okay. So along theta, I guess, so there's a Frobenius pullback, so I guess here I should put theta tilde, is the Hodge tape complex of X. Okay, so now assume that X over O is actually a base change of, let's say, S, but this one lives over ZP. So now, because of the integral Sen theory, developed by Bhatt Lurie, when P is large enough with respect to the dimension, I apologize, I forget this. So P larger than D in the theorem before, I should have assumed P larger than D. So there is a splitting of the Hodge tape complex as sum from I to D of omega I X, so the shift of differential shifted by I with a Borel-Kiesling twist. Okay, so now what do we do with this splitting? B. So I will call this the back Faltings map. Well, A omega x over O. So by definition,
So maybe you could say, what was Faltings doing? Something in Z space? What's exactly?
what is exactly Faltings' idea?
Yeah.
So he was, his argument, yes, is on the zero modular variety, but it's a general one. So his way of proving the Hodge state decomposition was to have this canonical extension of the sheaf of differentials by something, and then you have row inverse. Okay, so it's Falting canonical extension, and then he had a way of constructing this map by essentially pushing forward. So we will see later by pushing forward some sheaf on something that doesn't have a smooth mono to something that does. But we're going to see in just a minute how this formalism gives a clarification of how this argument works. So then,
I was just asking the context. It was Ziegler space.
yeah. But his extension is very general for any variety. But he wrote this argument in the case of Ziegler space, just
I'm
at
just
least
trying
as
to
far as I'm
remember
aware.
What you're talking about.
Yeah.
Where he doesn't win.
So this, you get a map from the R nu star of a inf x. But now if you reduce everything mod xi, then you get this to R nu star of O x plus. So there is a map from Hodge state O of x to R nu star of x hat plus. Did I take those? Yes. So actually, you get global sections of R nu star of O x hat plus. And now this is where the Faltings derivative comparison theorem comes in.
You didn't actually take global sections here, but
I don't.
I just mean like what's on the board on the right here. There's no global sections. So in your definition of the Hodge state complex on this board,
On this board, there's no global sections. No. Whoops. Okay. So I always get it confused. So okay. So in the end, after taking cohomology, so you get a map from the HD of let's say omega x I. So minus I to the HD of R nu of x plus, and this is where Faltings' primitive comparison theorem says that this is almost isomorphic, or this is an almost isomorphism to the etale cohomology. So in the end, so if you take, sorry, this here dot. So if you take dots on both sides, and I focus just on the case of the H0, so I get the map from the H0 of x omega d x minus I tensor with the maximal ideal of O. This is what a normal map is. I get a map to H etale of x zb tensor with O. Okay. But here, to use the splitting, I secretly assume that so here. here x is proper smooth. But now let's say that I have y above x, and this map, I call it pi, and then on the generic fiber y to x, this is let's say this is finite. Then I still have a map from the pullback of the Hodge complex of x to the Hodge complex of y. And now again, I can map this to my R nu star of y hat plus. And so since at least this isotope, so this is Faltings primitive comparison theorem. Primitive is also when y is not necessarily smooth. So since primitive comparison theorem holds for y, then you get the map from the h0 of y, but for the pullback of the differentials of the smooth guy to the hd etale of y zp. That's sorry, here I forget the varieties and twist. There's okay, so this is what I call the Bhatt Faltings map. So it says that sections, whatever integral structure you have here, well, it's essentially preserved in etale cohomology. At least when p is large enough. So how much time do I have? 2 minutes? So the key now, specialize this situation when, well, you have yr over x, which was y naught. So this has hyperspecial level at p. And so this one has an actual smooth model over zp. And then I guess y let's say yr is the normalization of x in yr. Okay. So now you're exactly in this situation. And so now you get the map from, so this is a lattice in modular forms, in holomorphic modular forms in the space of holomorphic modular forms of some level gamma 1 and p to the r to etale cohomology. So here I'm forgetting the varieties and twist. It adds a row and you have to deal with that, but you can deal with that after taking inertia covariance. So here I'm being sloppy because I don't have a lot of time. So you get the map like this, and now you have to compare the integral structure of Hida families, or rather of Hida families, meaning at finite level, this is just the Q expansion integral structure. With whatever integral structure this says. And the key point is that an ordinary form will have integral Q expansion at all the cusps in Y that are above the infinity cusp on X. Okay, so this is the key map that produces for you all the important etale cohomology classes. Okay. So and then this is the crucial. One of the crucial steps. And so when you're working on some more general Shimura variety, it's unclear how you should, what integral structure you should use on whatever p-adic modular form you have to be compatible with this sort of objects. But maybe the T expansion, the certate coordinates give you a good candidate, but we haven't explored this. Okay, I'll stop here.
Well, I guess you didn't say anything about what makes your theorem stronger in the Hilbert case rather than the Siegel case, and is it related kind of like to this last point about the Q expansion integral structure, or what?
No, it's just that so in the stronger in the sense that so for example in the case of Hilbert we can at least say that for a surface we get an isomorphism. This trivial even typus. For Siegel, we cannot say anything because of the H2. I mean, but it's but for at least for as before, it's very close. Yeah. Ellen.
So you can do UNN, but just not UNM for other signatures then?
Yeah, so you'd have to study.
I mean, for UNN, you'll still Q expansion.
Yes, exactly.
And they'll look similar, I'm guessing.
Yes. We haven't written it up for UNN, but yeah, you just have to be careful to use, what is the analog of gamma 1? So, for example, in the Siegel case, even for the Siegel modular variety, you can ask for, okay, are you at Borel unipotent, Siegel unipotent, and we prove the theorem for Siegel unipotent. So we can only move one weight.
Okay. Oh,
So the P bigger than D,
Yeah.
that's coming from Bhatt's work.
And also there's a row somewhere. So there is 1 over. So here, if you move this on the other side, you get.
You can't get, Faltings doesn't have that.
No, Faltings also does. Yeah.
Right, it does.
Yes, because of this guy. Okay, so rho is the 1 over. No. Okay. ZW minus 1, and so if when you take co-invariance, you can get rid of this guy, but sometimes this guy has a p in it. So if p is small, then you might lie of.
Okay, so it's
You might have p in the denominator.
already present there.
Yeah, it's already present in Faltings. Yeah, no.
Does this tell you anything new at finite level?
At finite level, yes, already at finite level, you can construct like this integral etale classes, just as images of this. So this tensor M disappears after you take inertial coefficients. So you can descend your coefficients to where things have, valuation, the image of the valuation is Z.
what were you saying about you can only vary one weight, like if you're looking at the highest weight, or when you were saying, I didn't catch.
Oh, yeah, so you can only vary, like, for example, in Siegel modular forms, you can only vary in parallel weight.
Okay,
So if you have a,
which for you, things are ordered so that's scalar or not scalar?
so if you're working on, I guess, yes, they would be scalar, yeah. So
Okay.
this will be everything scalar.
Okay, and so even if you're like, and then you were saying, so when you were in the Hilbert case, so you were saying it had to be still at every real place, had to be.
Yes, so the at each place, the weight should be the same. So
What's-
the
I didn't
ordinary.
understand, what was it, what's the abstraction to? Having, say you're like a quadratic.
So for the Hilbert case, I think it's the clearest. So if you take the nearly, so that would amount to taking nearly ordinary
Oh, right. you said
cohomology, and then now you don't have inertia invariance necessarily.
that. Okay.
So you don't listen.
Sorry, so this P bigger than D thing, I guess one place it comes like one way to say it is that that hypothesis ensures that the Sen operator is semi-simple, and then you're picking out an eigenspace for it. But could it, like, do you know that for Shimura varieties, when P is smaller compared to D, that the Sen operator is actually not semi-simple?
No, I don't know that. No. But maybe it's still true. But that I don't know. Like I would have asked you with the question. or Louis, yeah.
Does this behave nicely for restriction? Like if you take, say, GSP for D or something, and you put two G's in there or something?
Yes.
Assume this behaves nicely?
Yes. It should, because and this is this interval structure is asking for your T expansion to be integral of all the points above a point
Yeah.
in X.
So it should-
And so that is preserved, I think, under restriction. But I haven't checked this, it's just, so take it with a grain of salt, but I think that it's true.
Right, more questions? Oh, that's just Marco.